Hey everyone, good to see all of you. Thanks for sticking around to this. I think this is the last session on this stage today. So, what I want to do today is chat with you about democratizing AI and the role that I think data-centric AI will have in that. And today, I'm also going to show some technologies, some data-centric AI technologies that I've never demoed publicly anywhere else before. So hopefully, that'll be fun for you. If the demo works, you never know. So AI cannot reach its full potential until it's accessible to everyone. And AI has clearly transformed tech companies, especially consumer internet companies with hundreds of millions or maybe billions of users. But once we walk outside the consumer internet or the tech sector, candidly, development or adoption of AI feels very nascent. If you go to healthcare system or manufacturing plants or logistics network, there is some activity, but the activity there is so nascent compared to the consumer internet sector. I recently gave a TED Talk, which was just posted online yesterday, so you can find it online, where I talked about democratizing AI and how I hope someday even the owner of a small pizzeria who does have data, usually they do have data, can use AI to drive the performance of their own small business. But not even going all the way to a small locally owned pizzeria, even if you look at the largest enterprises outside the tech sector, why is adoption of AI so much, further behind compared to consumer software internet? What I want to do is share with you what I think are the two key barriers to AI adoption, and then share some ideas for helping all industries drive AI adoption. I know a lot of the theme of this Intel event has been openness, and I think a key part of lowering these barriers will be building that type of open ecosystem that empowers a lot more people to participate and to build and use custom AI systems. But first, one of the barriers to AI adoption is small data sets. And I've been doing a lot of work in computer vision, in manufacturing inspection. So I'll illustrate a lot of concepts with examples from computer vision. But the recipe I'm describing here today, I think applies broadly to many AI applications. And I hope that some of you maybe even take this recipe and go execute it in other domains in computer vision to help many more people adopt AI. But barrier one, small data sets. So when I was working for big consumer software internet, I once built a face recognition system using 350 million images, right? So I helped develop algorithms for what to do when you have hundreds of millions of images. I gave a talk at a manufacturing conference and asked, how many images do you all have? And it was a live event, and in the live poll, this was the audience's answer. The most common answer was 50 or fewer images. And so tech built for 100 million images, it just does not work when you have 50 images. And often in these other industries, 50 images is all you have. If you go to a smartphone maker, they just don't make millions of defective smartphones. So they may only have, thank goodness, they may only have dozens of defective smartphones for which they have pictures, and you either got to make it work with 50 images or else it's not going to work. Or in healthcare, works on medical images where we only have 100 images of a rare medical condition, and there are just, fortunately, no more patients, right, that suffer from that medical condition. So you just got to make it work with those small data sets. I think data-centric AI will be a key part to unlocking that value in all of these industries where the data set sizes are just much smaller. Second major barrier to widespread AI adoption that I see is the customization or the long tail problem. If you take all current and potential AI projects in the world and sort them in decreasing order of value, you would get a curve that maybe looks like this, where to the left are the single most valuable AI projects. So for example, maybe some company can hire hundreds of engineers to build a single system that serves more relevant ads, and that drives, frankly, north of $1 billion per year worth of value in some companies. Maybe the second most valuable AI system is some web search thing. Maybe the third most is some online shopping product recommendation system. But so in the AI world, we've collectively figured out how to build these large monolithic AI systems that can serve hundreds of millions or sometimes billions of users and drive massive amounts of economic value. And that makes it make sense to build a large AI team and do all sorts of things to just make that ad system or that web search engine or that product recommendation work. We know how to execute that recipe, and here in Silicon Valley, many companies, internet tech companies are executing that recipe, especially companies with a large user base of millions of users you can apply one AI system to. Once you go to other industries, the physics of the world makes the applications much more heterogeneous. For example, if you go to a pharmaceutical plant that is making pills, they may want a computer vision system to inspect whether the pills have defects on them, and only this one company makes pills, that looks like whatever they look like, and so they need a custom AI system. It needs to be trained on images of their pills. Down the street, you may find a plant that makes sheets of steel. And well, sheets of steel look totally different than pharmaceutical pills, so they need a totally different AI model trained on whatever sheets of steel look like and what dents in sheets of steel look like. And again, maybe in the next city over, semiconductor maker, makes semiconductor wafers, and they need their images. What they make is totally different, so they again need a custom AI system. So the AI industry-wide problem that I see and that I hope all of us can collectively find ways to solve is, once you're outside the consumer software internet industry, the physical world is heterogeneous. This is just different products. And so if there are 10,000 projects, from 10,000 manufacturing plants or other computer vision applications, and each of these projects can be a $1 to $5 million project, what I see right now is there are many, many of these $1 to $5 million projects that no one is actually executing on effectively. And how do we collectively get them executed on without someone like me trying to hire 10,000 machine learning engineers to go and execute on these? I was chatting with a leader of one of the large cloud companies who was leading a team, and he said to me, hey, Andrew, I only have a few hundred engineers. How do I get all these projects done with only a few hundred machine learning engineers? I think the only way out of this dilemma, which is the AI industry-wide dilemma, is to start to build vertical platforms to enable the end customer to build the AI system that they need. So rather than me hiring 10,000 machine learning engineers, can we set up the manufacturing staff in each of these plants to build the custom AI system that they need? And I think the most likely path to success, which I think, which is actually working, so I'm confident it'll work, is to set them up to engineer the data rather than the code. Because if you go to the IT personnel in the manufacturing plant and say, hey, everyone, I need you to write code to invent the next generation of a transformer neural network, that's pretty tough. But you provide to them tools that empowers them to express their domain knowledge about what is a good pill, what's a bad pill, what is a good sheet of steel, and to express that domain knowledge by engineering the data, then that is something that they are able to do, and that sets them up for success to build and deploy these AI systems. And a lot of that is the heart of the idea of data-centric AI. And just to be clear, even though I'm illustrating these examples using computer vision, this is the design pattern I see in natural language processing, see the same pattern in healthcare data, where imagine going to a hospital's IT personnel and saying, hey, invent a new neural network. That's tough. But if you say, oh, I need your nurses and doctors to label data to customize your AI for your custom EHR, electronic health records data, that is actually much more doable. So I sincerely hope that many of you maybe will take this recipe that I'm describing that is working in computer vision and really execute it in many other domains, because we need this to democratize access to AI and to open up these opportunities to a lot more people. So you've heard me say a few times now that I think data-centric AI is key to democratizing access to AI, but what does that mean? So over the last few decades, the conventional approach to AI development has been a model-centric or a code-centric approach. And by that I mean that to build an AI system, you need to write code to implement some algorithm or some neural network model, some deep learning model. And then you take that code and you run it or train it on your data. The way that most researchers have done work in AI for several decades was download a data set off the internet or get data from someone, And then, let's engineer our code. Let's work on the code, tune the neural network algorithm. Let's make the code work for the data set that we have. And nothing wrong with this. And in fact, this paradigm of development has driven tons of machine learning progress for the last few decades. But thanks to this paradigm of machine learning development, what I see is that for a lot of practical applications, the code is basically a solved problem. Not all problems, but for many problems, there's an open source implementation of something you can get off GitHub that will work just fine. You do need to understand it. It's good to know what you're doing and find a good model, do a robust hyperparameter tuning. But so long as you do that, what I find for a lot of practical applications is it's more productive to even hold the code fixed or find a great implementation of something, do a robust tuning, hyperparameter tuning of it, and to instead spend the time systematically entering the data that says, I see Greg nodding. I think as engineers, we've experienced this intuitively for a long time. They'll set up the team to get a successful AI system built and deployed much more quickly, much shorter time to value with this recipe. So data-centric AI is the discipline of systematically entering the data used to build an AI system. Let me share with you one case study. This is a project that we're working on with a plant that makes very large sheets of steel. So your car, if you own a car, was made out of these giant sheets of steel at one point, and so we're working on a plant that makes these sheets of steel. Manufacturing plants internally, their internal tech team had achieved 76.2% accuracy on inspecting sheets of steel, and they wanted 90% accuracy based on the performance of their human inspectors. So a few large AI companies went in and took their data set and spent months filling the model, tuning hyperparameters, trying different neural network architectures, and basically none of it made any improvement over baseline. One of my engineers went in and provided to them our tools, our data-centric AI tools, and in, I forget, is it 2 weeks or 3 weeks, definitely 3 weeks or less, was able to surface inconsistencies in the data to empower the subject matter experts in this manufacturing plant to relabel the data so that with high quality data, in just a few weeks, they're able to achieve the performance milestone that they wanted. So working on this project, this was actually several years ago now, one of the lessons I learned was that taking a data-centric approach, it empowers or allows subject matter experts, the people that work in the steel plant that really know what is a good sheet of steel, it empowers them rather than only the machine learning engineers to prepare data. And given that there are so few machine learning engineers in the world today, I hope there'll be a lot more. I think this is key to democratizing that access and opening up access to building AI systems to a lot more people. Now, you've heard me use this phrase a few times, engineer the data, systematically entering the data, data quality and so on, but what does it really mean? Data is data, right? Why would you engineer it? How could data go wrong? So let me just illustrate with a few examples. It turns out that data, even data labeled by experts, highly motivated, highly skilled, have been doing this for years and the world's best experts at something, even that data is often inconsistent. And I've seen this in large companies, small companies, is very surprisingly pervasive. Here's one example. Experts will often label the same thing in different ways. So this pharmaceutical pill, not at all uncommon for one expert that maybe has been inspecting this for years, is even supervising others. One inspector may say, oh, this is a chip. And the second inspector says, this is a scratch. And I actually don't know who's right, since I'm not a subject matter expert. But this inconsistency makes the task of detecting chips and scratches very confusing to an AI system. The AI system will look at this data and go, I don't know what's going on, and it will fail to detect chips or scratches. One of the lessons I've learned working with many companies on their data issues is when you spot an inconsistency like this, almost any consistent standard is better than an inconsistent one. So call it chip, call it scratch, either one's fine. But driving to that consistency makes a big difference in machine learning performance, and it's critical also to having performance of a small data set. If you have 100 million images, then fine. The learning algorithm will take an average and maybe it's called a chip somewhat more often. But you have only 10 images or 50 images, that consistency is critical to making your application work. Some other examples, bounding box size. We often ask people to draw a rectangle around what you want to find, to computer vision tasks. So one labeler may say, oh, that's really discolored. Second may say, that's discolored. Neither of them is wrong. Both of them are hardworking, motivated, doing a good job, but this inconsistency, which is really kind of no one's fault, right? This is very confusing. This is another one we see very frequently in multiple applications. Bounding box sizes. One labeler will label, we say, please use the bounding box to indicate where the chip is. One labeler will do that. One labeler will do that. And this inconsistency makes the data very confusing to a learning algorithm. And again, to be clear, I see the same thing in natural language processing. People look at the same snippet of text and render different judgments. I see the same thing in audio. I did a lot of work on speech. Experts will transcribe the same audio clip very inconsistently, right? And this is a pervasive phenomenon. So what I want to do is show a quick demo of a tool we've been working on called agreement-based labeling to help developers, let's see if this works, help developers spot these inconsistencies. Oh, and by the way, I know that yesterday we saw Intel's Getty presentation on Intel's take on the computer vision task. I think it's actually really great that multiple organizations are approaching the computer vision application and collectively trying to solve this for everyone. And I want to share with you my take on it, which is a data-centric and tooling kind of view on it. So let's see. So this is a, I don't know, UI, right? Sort of what you expect for uploading images and labeling images. I actually labeled these images last night for this demo. But if you suspect that your labels may be inconsistent, one of the things we do, what this tool does is we invite you to ask different labelers to label just a small handful of images. And if you do that, then you can aggregate statistics. So this is data labeled by me, Nicole, Michael, 3 test accounts. But by doing that, you can then look at statistics of how much labelers agree and disagree. And some of you think, I know crowdsourcing, you get them to vote, right? No, we don't get them to vote, but let me explain what we actually do, which is here, I've computed the agreement score. So this is an image with high agreement score, meaning that, I labeled that as a discoloration, Nicole labeled this, Michael labeled this, so very high agreement score. So it looks good. Looks like we actually agree on discolorations. Scratch, I labeled this, Nicole labeled this, Michael labeled this, right, and so on. It's automatically selected Nicole's label as the most representative, so we have to pick one label of go with Nicole's. But more interesting is if I sort this in decreasing order to look at where the highest disagreement is. So I had labeled this with 2 bounding boxes, Nicole with 1 bounding box, totally fine. Michael labeled it with 1 bounding box, because there's a defect. Why do you need to flag both of them? And so what we found is that this type of labeling protocol, we don't say, let's get 7 people in a labeling team somewhere to label millions of images and vote. If you're a large tech company with hundreds of labels, maybe that's okay. But when you're small data sets and you want things to work on small data sets, the more fruitful process we've found is use a tool like this to help you efficiently figure out where are the inconsistencies. And in this example, the inconsistencies is on these images, on how we label chips, but not on how we label structures and discolorations. And what a tool like this does for you as a developer is it allows you, instead of trying to improve all the data, which is too much data, what am I supposed to do? It helps you focus your attention on the slice of the data, meaning the subset of the data where there's an inconsistency that is then a good use of your time to collect more data, improve the data quality. And that, rather than just, let's get these people to vote, that allows teams to drive much faster improvement to the performance of the algorithm. Right? So I've shown just one example of one tool to execute the data-centric AI development workflow. I want to share with you how I think about machine learning workflows and how a data-centric AI tooling orientation hopefully makes teams more efficient, shortens time to value, improves quality of the models you build. So you may have heard that machine learning development is a very iterative process. right? So you train a model, and then when I train a machine learning model, it never works the first time, right? Maybe once 3 years ago, it worked once for me, but basically never works the first time. So the standard workflow for machine learning is train a model, and then you carry error analysis to figure out the ways you wish it was doing better. And then in the past, many people would say, oh, let's tune the model, change the hyperparameters, pick a different neural network, switch the algorithm, and then you train the model again, and you kind of go around this loop over and over to drive improvements. One insight that I want to share with you is if you're developing a machine learning model, the workflow of developing a machine learning model, it feels much more like debugging than development. And if you approach machine learning development with that mindset, then I'm going to build a model that's not going to work the first time, and then most of my time is about having systematic ways to debug it. I found that teams with that orientation end up making much faster progress. So with a data-centric AI philosophy, what we do is instead of tune the model, we find ways to improve the data, where error analysis will tell you, oh, the chips is where the labels are inconsistent, so let's improve the data there. But discoloration is fine, let's not waste time there. And tools to help you improve the data quickly is critical for efficiently improving the performance of your machine learning system. And as part of this philosophy as well, I don't really like the term data cleaning, because there's this implication that you clean the data and then you go do the real work of machine learning. But data cleaning is not like that. Data cleaning is not a pre-processing step that you do once before you go on to do the real part of machine learning. Instead, I think data cleaning, or really improving the data, is a core part of the iterative process of building a machine learning system. And what we need is better tools and frameworks for making that efficient. So in what I showed in agreement-based labeling, previously or for a long time, frankly for decades, it would take sometimes a skill and sometimes luck of an experienced machine learning engineer to spot inconsistency in the data, and then we fix it. Sometimes through skill, sometimes through luck. But if we're more systematic about this, then that's how we open up access to a lot more people. And so to talk about iterative nature of machine learning, there's a second framework that I hope will be useful to all of you as you build machine learning systems, which is when you're planning on a machine learning project, to think through the life cycle of a machine learning project. And here's what I mean. So the machine learning world, mainly because of the fantastic innovations in academia, has focused a lot on how to train a model, how to take a data set and train a neural network or train a model on it. But if you're building a practical system, I find it more useful to not just think about training a model, but to plan out the entire life cycle, which starts from scoping a project. So I might, talk to the partner or customer and make a decision to inspect pharmaceutical pills, so to decide what to do. And then there's the initial data collection. How do you decide, how do I take pictures of this thing? How do I label this thing, right? After you've collected the data, you then train a model, and when you find it doesn't work as well as you hope, you then go through this iterative process of going back to often collect more data, improve the data. And you do that a bunch of times until your model is good enough that you want to push it to production deployment. And then after you deploy it, you find that data in the real world changes, the plant uses a new material, something changes about lighting, concept-driven, data-driven, right? The data changes. And so after you've deployed in production, you still have to often monitor and maintain and update the model by feeding data from the production deployment back. So bearing in mind that machine learning development is a very iterative process, I find that to be effective at executing these projects, one of the things that really helps is if you can work through the machine learning development process quickly. So rather than spending 6 months to get to your first proof of concept, if you can spend weeks or even days or even minutes, maybe tens of minutes, to build your first machine learning model, it lets you get into that development debugging loop much faster. So one of the things I spent a lot of time, kind of thinking through is how do we make it possible for someone, including either like an advanced machine learning developer or subject matter expert, to very quickly build, deploy a machine learning system so you can get into this development loop. So let me show a quick demo of that. So this is a second application of food inspection. So actually, we actually work with food manufacturers, but many food manufacturing companies will want to inspect the food to make sure there aren't foreign particles inside, the food product that they're making or selling. Um, and so, let's see, just to show you the entire workflow, right? It's a bunch of images, drag and drop images here to upload them. I already uploaded it last night, so I'm not actually going to upload it. And then with images, so this is a common machine learning workflow, but I'm going to show you how I'm doing this, right, kind of in seconds. Nothing to label here. Let's see. And so I find that the ability, and this is really, when I work on a practical machine learning system, I'm really like sitting on my laptop and doing pretty much exactly what you're seeing me do in seconds. Drag and drop images, draw a bunch of bounding boxes to label them. I label 4 images, and I label the rest. There are 50 images. I labeled them all last night, and then hit a button, and this starts training a model. This does take a few minutes, sometimes many tens of seconds, but just to just to not wait like a few minutes. I should train the model last night. Right, so it's a trained model with the same data set that I had labeled last night. And then I find that there's a lot of error analysis I tend to do because frankly, my machine learning system, the first time I build it, it never works as well as I want the first time. And so there's a lot of error analysis tools, things I used to do manually. Right, look at images, fire up, like a spreadsheet to count errors, use a Jupyter notebook to visualize images, or even frankly, use my laptop image viewer to visualize images. So thinking a lot about how to build tooling to make these visualizations efficient. And so, model performance statistics, it's not perfect. It looks like I made one mistake on the dev set, so you can click on that. But I'm going to show you what happens if you take a trained model and deploy it, right? So this model I trained last night, and actually that's pretty much it. Where's my test set? And then, and then if you want to run inference, right? It's kind of that's pretty much it. So again, I didn't label 50 images. I didn't drag and drop 50 images, upload it for you. But what you just saw, I actually, when I pulled this over, I thought there was 1 screw. It actually has 2 screws. So this is a real demo. I'm not like, I honestly, I thought I had using the image of 1 screw, right? And then we just did inference, and I just found out something about this image. And then also, I talked about closing the loop of the machine learning process. So there's that image that I used just now. And one of the things that's really important is not just deploy a model and then say you're done. Deploy it after it's running, in a real-world production environment. You often want to feed that data back to your training set. And so if I want to take the image we just used, and maybe I ran this one earlier this morning because it's testing it, and take the data from the production deployment, and if I click Add to Data Browser, this adds the data back to the training set, so you can select what data to close the loop from the production deployment, so that you have tools to keep on improving your machine learning system through the entire project lifecycle, right? So, so getting into the machine learning development loop quickly lets you make fast progress. And the next step is, how do we systematically improve the data set? And it turns out, even the most revered data sets in AI have errors. So the ImageNet data set, kind of seminal data set by my friend Feifei and the team, this image was labeled tub, right? Looks like jeans to me. This was labeled a passenger car. Looks like school bus to me. Or even the MNIST data set, this was labeled 8. I don't know. Looks like a 9 to me. Or Amazon reviews, like that looks like a 5-star review, not a 1-star review to me. These are examples I took from Northcutt et al.'s work. So if even the most revered data sets, these are the data sets that, I don't know, thousands, tens of thousands, maybe hundreds of thousands, I don't know, so many research has been working on for so many years. Even these data sets have decades in them. Even these data sets have errors in them. I think the reality is many of our data sets have errors in them. And so rather than relying on just the skill or luck of an experienced machine learning engineer to find errors in the data set to fix it, I've been excited about, can we build tools to make the application of these ideas more systematic? So let me show you a quick demo of that too. Oh, right, again, so the tool is actually, go back to the data browser and then ask it to check label quality. This takes minutes. So again, ran this yesterday. And if you ask the algorithm to check label quality in this data set, it has 2 label suggestions. So let's review them. And it turns out that when I labeled this data set, there was a tiny screw here that I just forgot to label, and this one hidden beneath the serial, right, that I just forgot. And the basic algorithm is if the algorithm thinks that you omitted a label, right, then it'll suggest it to you. So then you can then accept the suggestion if you wish, or dismiss it if you don't agree with the suggestion. And this drives an efficient workflow to help improve the quality of the data. So, I often think about the process of rolling out new technologies. In fact, backstage earlier, I was chatting with Pat Gelsinger, who was telling me, some of you probably don't know this, but Pat, years ago, he was like the guy instrumental to the openness of the USB standard, openness of the Wi-Fi standard. And so actually, frankly, for years, I've personally been, frankly, really grateful, right? I have warm, fuzzy feelings to Intel for the work that Intel did years ago to open up the USB standard, because that created so much open innovation that so many more people could participate in building devices that just magically plug into each other. And I think for those of you that don't know, I think that a lot of that openness, we frankly have Pat to thank. A lot of it is Pat, frankly, going to argue, strenuously with another hero of our world, Steve Jobs, about opening up these standards. And I think that impact has been so large on our world and our community. And so to continue to hear Pat and Greg talk about open innovation, building these open ecosystems, that really warms my heart and it gives me a bright, optimistic a picture of the future. We can encourage a lot more people to come and participate in tech and in the AI world. So just thinking back about world of new technologies, including USB and Wi-Fi, but I'll use some examples I'm familiar with. This is what the world of a new technology sometimes looks like, right? Which is if you have a new software idea, initially you have some experts that manage to get something to work, right? And maybe let me share things I'm familiar with. The rise of deep learning. So about 15 years ago, there was a bunch of people that could get deep learning algorithms to work, kind of because we'd done it for years, we knew how to tune the learning rate or set this or set that, and so there are a handful of people that could get it to work intuitively. And then eventually the principles become widespread. People publish research papers, so the ways to get a neural network to work become widespread, and many more people are now able to implement a neural network in C++, right? Still error prone, but more and more people could get it to work. And then eventually, there start to be tools like TensorFlow and PyTorch to make the application of these ideas more systematic. So where we are in data-centric AI is, I think that we have been here for a long time. For many decades, there have been machine learning people engineering the data, happening for a long time. The data-centric AI movement has been gaining a ton of momentum the last couple of years. So I think we're firmly in this stage now, where there are many workshops, events, and so on that many people are organizing to advance data-centric AI technology. We're starting to see some standardization of terminology, and the principles are becoming more widespread. And one thing so I organized a NeurIPS workshop last December, for example, with collaborators on data-centric AI. There's a lot that's going on now. And one thing I'm passionate about is to also build tools to make the application of these ideas more systematic, because then that tooling allows a lot more people to apply these ideas in a systematic and more error-free way. And so the project what I've been working on for several years at Luminary AI is software to make computer vision easy. And just to share with you the challenges, some of which I think we solved, some of which we continue to wrestle with. Data is messy, right? There are a lot of data problems, but you saw me talk about inconsistent labels and incorrect labels, right? Just missing a label outright. Or sometimes images are low quality. We did a bunch of work with medical imaging where the images were blurry or they're poorly imaged. Can we fix that? Or sometimes we have insufficient types of, insufficient data of certain types. Done work with aerial imagery, where you have enough pictures of this, but you need more pictures of that. So can you focus your attention on getting more pictures just where you need it? Data changes in deployment, so it's important to close that loop after you've deployed it to bring it back to keep on training. Many of us need help prioritizing labeling resources. If you have a lot of data, well, where do you want your RC labelers to label the data? You don't want to label everything, but what's the most effective use of limited labeling resources? Data augmentation or data synthesis, handling metadata, handling data cascades, where you have complex chains of multiple models. So there's a huge, many issues here yet to be resolved that, frankly, I hope all of us collectively can keep on working on. And even though I've illustrated this with computer vision, every single bullet point here equally applies to, I think maybe almost every other domain in AI, and I hope that all of us collectively can figure out how to build the principles, develop the principles, and also build the tools to let a lot more people access and build their own custom AI systems. So with what I'm seeing with data-centric AI, I talk about democratizing access to AI, but what I see is that teams can more systematically improve data, where by teams, I mean it's not just the machine learning engineer, but the subject matter expert and multiple stakeholders, or even global teams working in a geo-distributed way can collaborate to figure out what is a defect, or what is this thing you're trying to find in your aerial imagery, or what is this categorization of online images that you want for your e-commerce retail application, what have you. Definitely shortens time to value, right? So now, when I build a machine learning system now, I actually get annoyed at myself if I can't build the first model within an hour, right? Sometimes it's even minutes, but I think it's good to get that first model built and maybe even deployed very quickly, and then to improve it from there. And then also track and reflect post-deployment changes, which are mainly when the data in deployment changes. Just to wrap up, just a couple more slides. AI is changing all industries. You may have seen this widely cited study by McKinsey estimating $13 trillion worth of annual value creation through AI. And a lot of this value is in sectors outside consumer software internet. There's things like retail, travel, transportation, logistics, automotive, materials, and so on. Candidly, when I speak with leaders and these CEOs of these different other industries, I'm not seeing it. It's not yet happening, right? All of these other industries are still at a much earlier phase of AI development. And I think the two big barriers to this are small data sets, as well as that long-tail customization problem, which is why I think data-centric AI will be key to unlocking AI's full potential and to taking it to all of these industries to create much more value than any of us that our community has ever managed to create just so far. So just to wrap up, data-centric AI is the discipline of systematic entering the data needed to build an AI system. I think this is a very important technical direction for the AI community to flesh out. And by addressing small data and conservation problems, I think it's key to democratizing access to AI. Just to mention some resources, the Batch is a weekly newsletter that one of my teams publishes, in which we try to share what matters in AI right now. And I'll often try to share what I think is the latest, in data-centric AI, to share useful insights. Data-centric AI Hub is a website that many collaborators and I have been working on. All the videos, all the presentations from last year's NeurIPS, Data-centric AI workshop are also up on this website, but a lot of free open resources and thought leaders, like various academic and really leaders in the technical field of data-centric AI have been writing articles there, for example, and then Landing AI is where we've been building tools to make computer vision easy for this. I should have mentioned, a few of us from Landing AI are here today. So actually, sitting in the front row, Dan Maloney, Scott McCracken, and Grace. So yeah, they're sitting up here. So I think we're actually all going to be around for. Thank you. Thanks, Pat. Yeah, Pat sounded that. Thank you. Yeah, so a few of us are around for a little bit and just eager to meet with all of you and get to know you and see how you can keep on building this open ecosystem collectively. And so just to wrap up, I'm really happy to have had an opportunity to speak here today. Oh, and also I just want to reassure you, I am using a Mac. This is an Intel Mac, Core i9. And just when I actually bought this Mac, I deliberately chose one with Intel inside. So just so you know. But I'm excited about the open ecosystem that Intel is leading, and very glad to be a part of it and here with all of you. And I hope that one small contribution I can make is to help us all collectively move toward democratizing access to AI, which I think will benefit through everyone. And one important avenue for doing that, I think, is data-centric AI, which I think is key to unlocking this next era of AI. So let me say thank you all very much, and thank you.